Hello everyone. This is lecture 7, Markov change. So for this lecture and the next lecture, lecture 8, will be dedicated to the applications of matrix operations. So in this lecture, we're going to focus on Markov chains. In the next lecture, we're going to focus on cryptography. So the learning objective of this lecture is to use a stochastic matrix to find the end state matrix of a Markov change. We're going to define all of these terms later on in this lecture. And then at the end, we're going to find something called the steady state matrix of a Markov change. Okay. So the applications we want to focus on is the state of populations, because for example, you have resident of a city may live in downtown or in a suburb. You may have voters may vote for the Democratic Party, Republican Party, or Independent Party. So they have different states of the voters, right? So some voters can vote for one party, the other voters can vote for another party. Also, there's consumer may like to drink Coca-Cola, may like to drink Pepsi-Cola or another brand, right? At the same time, all of these cases or all of this state can be switched around. So that means the consumer may drink Coca-Cola today, but later on in the week, for example, they switch the states and they want to try Pepsi-Cola or another brand, something like that. Or someone who used to drink Pepsi-Cola and then later on they decided they want to try Coca-Cola, then they can switch the state as well. And the probability that a member of a population will change from a certain state to another state will be defined as the notation P sub ij, right? So that means that is the probability of the member of the population will change from the J state to the I state. So again, this is P sub ij. So this is the probability of the member of the population will change from the J state to the I state. Okay, so that's how it's defined for this particular context. And because this is the probability, usually, it is defined that P sub ij is always between 0 and 1, right? So for P of ij equal to 0, that is that the member is certain not to change from J state to I state. That's the probability equal to 0. When the probability equal to 1, then the member is very certain, very sure that he or she will change the state from J state to the I state. So the member is certain to change from the J state to the I state. Okay, and because we may have multiple states in the populations, so anytime you define a probability, you can put that probability into a matrix, right? And it can be defined as follows. So this is the n by n matrix, right? So we define as follow. So for the number of row, it's gonna be the probability that the state that you start with, right? So this is state 1, state 2, up to state n, and you say this is from, right? Because you're starting from this particular state, and then you later may switch to another state, and this row are defined to be state 1, state 2, to state n. This is where you end up after you make the change in the states, okay? And this matrix P is called the matrix of transitions probabilities because you can make the transition from one state to another state. So P is the matrix of transitions probability. Right, because all the entries in this matrix consist of all the probability of the member changing from one state to another state. All right, so a further explanation is that this matrix gives the probability of each possible type of transitions or change within the populations. Okay, so for example, in this one, let's pick out one probability here. So P sub 1, 2, that means that this is the probability of people or the number in the populations in a state 2 switch to state 1. Okay, so that is just one example, right? And again, because all of this probability, all the entries in the matrix are probability. So one condition that we need to impose on this particular matrix is that the sum of the entries in any column of P has to be 1. Okay. So one condition here that the sum of the entries in any column of P is equal to 1. So that is, for example, you want to look at the first column here. That is P1, 1 plus P2, 1 plus P3, 1, so on and so forth up to Pn 1 had to add up to be equal to 1. Okay, so that's the conditions, and therefore all of these conditions combined will create something called stochastic matrix, right? In addition to another name, that matrix of transitions probability, so that it's indicate that all the entries are just the value of the probability from switching one state to another state. Then you impose another condition is that all the entry of any column or the sum of the entries in any column of P is equal to 1. With these two requirements, you have stochastic matrix. So a stochastic matrix is a square matrix when each entry is a number between 0 and 1. Again, because this number are probability. So, and the sum of the entry in each column of P is equal to 1. All right, so that's enough with the definitions, right? So let's quickly recap what we have here. So what we want to do is we want to look at the matrix. This is called the matrix of transitions probabilities, or more a stronger statement, P is a stochastic matrix because it's a square matrix that consists of the number between, or the entry is between 0 and 1, and the sum of the entry in each column of P is equal to 1. All right, so let's move on to some example to identify which matrix can be classified as stochastic matrix and which matrix cannot be classified as stochastic, cannot be defined as stochastic matrix. Okay, so this matrix right here is a stochastic matrix because the number is between 0 and 1, and the sum of any column in, or the sum of each column in the matrix add up to 1. Similarly, in this case, is the 2 by 2 matrix. The number or the entries between 0 and 1, and the sum of each column is also add up to 1. Similarly, in for this particular case. Moving on to the next 3 example of matrices. Even though what you have for the entries are such that the entries are between 0 and 1, they do not add up to 1, right? So each column or the entry in each column do not add up to 1. So for example, 1/2 plus 0.1. So this is 0.5 plus 0.1, which is 0.6. It's not add up to 1. This is 0.4 plus 3/4, even though it's add up to 1. Because of these issues, because of this column that didn't get add up to 1, then you cannot classify that as a stochastic matrix. Similarly for this case, in this case as well. Right, so hopefully you get an idea how to classify a matrix to be a stochastic matrix. Okay. Now, with this stochastic matrix, tell you a lot of information about the interactions or the change of the state, right? Or rather, the Markov change of the states. Okay, so if again you identify the column or the state at the beginning, right? So you have this is state 1, state 2, stage 3. You're starting by staying in this state, right? And then later you may change your mind and switch the state. So this is state 1, state 2, state 3. This is where you end up with. Okay. So this number 0.4 tell you what? Tell you that this is the probability of the member switching, or the member in state 1 stay in state 1. This number 0.5 tell you that the member, there is 50% of 0.5, 50% chance that the member in state 1 will switch to state 2. This number 0.1 means that there are 10% that the member in state 1 will switch to state 3, and so on and so forth. Okay, so let's try another example here. So 0.3 is the number, or there is the 30% chance that the member in state 2 will switch to state 1. Okay, so hopefully you get the idea. Right. And then you can map this number into the schematic of states, right? So there are 3 states that we need to look at, right? And for each state, there's multiple interactions here. The member in state 1 may stay in state 1. And the member in state 1 can switch to state 2 or can switch to state 3, right? It doesn't matter. Similarly, for the case of state 2 and state 3 as well. Now we're gonna map this number to the schematic, right? So the member in state 1 remain in state 1, so there are 40%, or there's 0.4, so I can try with 40%. Right. And the member in state 1 can switch to state 2, so there is 50% chance that could happen. So 50%. Okay. And the member starting in state 1 may switch to state 3, and there's 10% that could happen. So this is 10%. Okay. Now you've done with state 1, you move to state 2. So in state 2, the member start in state 2 can switch to state 1, and there is 30% change that could happen. So state 2 change back to state 1, so 30%. Okay. And the member in state 2 remains in state 2, so this is 30% as well. Right. And in the last case, the member start in state 2 can switch to state 3, and there's 40% chance that can happen. So 40%. We're done with stage 1, we're done with stage 2, move on to stage 3. So in stage 3, right, the member can switch from stage 3 to stage 1, and there is 30% change that could happen. So 30%. The member stay in stage 3, switch to stage 2, and there's 20%. And the member remained in the same stage 3, and there is 50% change that could happen. Right. Now you can go back and forth between the transitions matrix, matrix of transition probabilities and the schematic given to you here. You can go back and forth like that to understand the transitions of the state. Okay. And one more conditions that we need to check to make sure that the matrix we are working with is the stochastic matrix, that the sum of each column add up to 1. Right, so in column 1, you have that 0.4 plus 0.5 plus 0.1 equal to 1. In column 2, you have 0.3 plus 0.3 plus 0.4. This is equal to 1 as well. And 3 in column 3, you have 0.3 plus 0.2 plus 0.5 is equal to 1 as well. And therefore, you let this equal to the matrix P. Therefore, P is a stochastic matrix. Okay, and it's very useful to understand the stochastic matrix, or to form the stochastic matrix, because it will give you some idea how to do the calculation to make predictions in the future. All right, so let's see how it get used in the following example. All right. So in this example, you have two competing companies offer satellite television service to a city with 100,000 households. In this, you are given a schematic or a figure shows the change or the transitions in satellite subscriptions each year. Now, to begin with, the company A has 15,000 subscribers and company B has 20,000 subscribers. Okay. They want to know that after 1 year, how many subscribers each company have in one, right? Have in 1 year. Okay, so there are 3 states in this particular situations, right? Even though you are dealing with just 2 companies, but there are 3 states, right? One state that there are subscribers using company A. The second state is there are subscribers using company B. And there's another state that nobody use any either the company, right? So, or there's no satellite televisions at all. Okay. So 3 states, and the transition from one state, or the probability of transitions from one state to another state, are given in this schematic or figure. What you need to do is you need to translate this information from the schematic and put that in the matrix of transitions probability. Okay, so what I'm going to do is I'm going to set up a matrix P. All right, so this is matrix P, and what from my experience so far, whatever I got for the column, right? That will be starting with state, let's say A, B, and there's none. That means there's no one using the satellite televisions in the city. And the subscribers start from this column, and then later they may switch to another services, right? So this is A, B, and none. This is where they end up with. All right, so if the subscriber using company A, there is 70% change that they use in the same company again after 1 year. So that would be 70% or 0.7. Now in state 8 again, after 1 year, the company or the subscriber can switch the company from company A to company B. So there is 20% that could happen. So that is 0.2. And there is 10% chance that someone who using company A can decide to cancel the subscriptions altogether and use no satellite televisions. And there is 10% chance that could happen. So this is point one. All right. Now for company two, you move on to the second state. Now a subscriber using company B may switch to company A, and there is 15%, right, or 0.15. Next, the subscriber using company B can decide to stay with the company B, and there is 80% chance that could happen, so 0.8. And someone who using company B can be cancel all the subscriptions and decide to use no televisions, satellite televisions at all. Decide not to use satellite televisions at all, right? So there is 5% change that could happen, or 0.05. And if someone who are not using satellite televisions at all may choose to use company A, and there is 15% chance that may happen. So 0.15, they can switch to company B, and there is 15% change as well. Or they can decide that, okay, I don't want no satellite for another year and see what happens. So there is 70% chance that could happen. Okay, so this is the matrix of transition probability. Now we need to add another conditions in that each column add up to one, right? So this column obviously add up to one, this column as well, and this column as well. So therefore you say that P is the stochastic matrix. Okay, so hopefully you get the idea how to translate the information given in the schematic into the stochastic matrix. Okay, now go back to the example and try to answer the questions that how many subscribers will each company have in 1 year? Okay, so what we need to know is we need to start with something, right? To start with some informations that at the beginning, what is the initial conditions? And the initial conditions or the initial value are always given to you, right? And the initial information given to you here is that the total number of household is 100,000. And the company is starting with 15,000 subscribers, and company B has 20,000 subscribers at the beginning. So that all of this information can be put into something called the initial state matrix. So initial state matrix represent the portion of the total populations in the three states Okay, so this initial state matrix is denoted as a capital X sub 0. So we start with company A, right? So the first entry is A, the second entry is B, and the third entry is none. And the first entry is for A, 15,000, right? So this is still a probability, right? But you are very certain that you have 15,000 subscribers for company A. So you use 15,000 divided by 100,000 household or subscribers, and you're going to get 1.15. Okay. Similarly, for the company B, you have 20,000 subscribers, and you compare that with 100,000 household. Then you use 20,000 divided by 100,000, or find the ratio of that, and you will get 0.20. Right. And the remaining populations, right? So you have 100,000 minus 15,000 minus 20,000 will give you 65,000 households who are not using either the company, right? And therefore, in the last state, the non-state right here is going to be 0.65. Okay. And usually, again, the initial state matrix, the information related to the initial state matrix will be given to you in the problem. Okay, so you want to calculate the portion of the population in the three states after 1 year, right? So given this initial year, what is the portion of the populations in the three states after 1 year? So what we were trying to do is we're trying to calculate x sub 1. So the portion of the population in the three states after 1 year. And it can be done by using the transitions matrix of the stochastic matrix. So you have 0.7, 0.15, 0.15, 0.2, 0.8, 0.15, 0.1, 0.05, 0.70, multiply with the portion of the populations in the three states at the beginning. So 0.15, 0.28, 0.65. And right, so it can be done that. Right, so the first entry is going to be 0.7 times 0.15 plus 0.15 times 0.2 plus 0.15 times 0.65, right? And the second entry is 0.2 times 0.15 plus 0.8 times 0.2 plus 0.15 times 0.65. And the last entry can be calculated as 0.1 times 0.15 plus 0.8 times 0.2 plus 0.70 times 0.65. And if we do the calculations correctly, we're going to get the first entry to be 0.2325. The second entry is 0.2875. And the last entry is 0.48. Right. So in 1 year, right, so company A, right, what you're going to do is you take this number and multiply by 100,000. So you get 0.2325 times 100,000. And you get about 23,250 subscribers, right? And after 1 year, company B will have 20.2875 times 100,000 equal to 28,750 subscribers. Okay, so that's the example. It's really a very realistic example that that help you to predict the future, right? So after 1 year, the company has this many subscribers, and the company B has about 28,750 subscribers. Right. And now using this information, you can actually calculate for the portion of the population in the three states after 2 years, after 4 years, after 5 years, so on and so forth. However, whatever setup we have is only give you the informations of 1 year at a time, right? You need to calculate x1 to get x2, you need to calculate x2 to get x3, so on and so forth. What we need to have, or what we want to have, is a formula so that you can calculate for the value of the state or the matrix of the state such that given any year or given any time, you can directly calculate the matrix, right? Without going through each number in the sequence. Okay, and that is called the end state matrix of a Markov chain. So the end state matrix of a Markov chain for which P is the matrix of transitions probability and X sub 0 is the initial state matrix, right? So the X sub n is equal to the matrix of transitions probability raised to the power n times the initial state matrix. So for n is positive. So let me be careful here. A positive integer. Right, so n equal to 1, 2, 3, so on and so forth, given the initial state matrix x0. Okay, so how could you actually obtain this particular formula? So we'll start with what we know. To calculate x1, you need to use the matrix of transition probabilities multiplied with the initial state matrix. And then you get the value of x1. Then you use that to calculate x2. So it's the same thing. Take the matrix of transitions probability multiplied with x1. But x1 is equal to p times x0. So you get bp times p x0 or p squared times x0. Now you get the value of x2, you move on to x3. So that is equal to p times x2. But x2 is equal to p squared times x0. So p times p squared times x0 give you pq times x0. Now, you can continue working out the details of x4, x5, x6, so on and so forth. But at this point, hopefully you recognize the patterns that for x sub n, you get p to the power n times x sub 0. And that is the end state matrix of a Markov change. Okay. Now moving on to a very similar example that given some information, you're going to put the information into a schematic and use the schematic to translate the schematic into a matrix or a stochastic matrix, and use the stochastic matrix to make some predictions in the future. Okay. So for this model, this is called the weather model. Right? So there are 3 states of the weather that are considered in this particular example. That is sunny, cloudy, and rainy. Right? So I'm going to put that sunny, cloudy, and rainy. Okay. And they say that if it's sunny one day, then there is 40% chance it will be sunny the next day. So there's 40% chance that could happen. And a 40% chance that will be cloudy the next day. So 40% chance that could be cloudy the next day. And 20% chance it will be rainy the following day. So 20% chance that could happen. If it is cloudy, so that's we're done with the first statement. The second statement is that now if it's cloudy on one day, then there is 40% chance it will be rainy the next day. this is 40%. And there is 25% chance that will be sunny the next day. So 25%. And there is a 35% chance it will be cloudy the next day. So it may stay in the same conditions, cloudy conditions. So it's 35%. And if it is rainy one day, then there is a 30% chance it will be rainy the next day. So there is 30%. And 50% chance that will be cloudy the next day. So cloudy, 50%. And 20% chance it will be sunny the next day. So 20%. Okay. Now you've given some information, you translate that information and put that in this schematic or the figure here to illustrate the probability of transition from one state to another state. Now let's map this information to, or put this information in a matrix. So you want to form this matrix of transitions probability. Remember, there are 3 states, and you start with the state of sunny, cloudy, and rainy. Right? So you're going to start here, and later you may end up somewhere here. So sunny, cloudy, and rainy. Right? You start at one state, you may end up at another state. Okay, so if the days is a sunny day, there is 40% chance that will be sunny again. So that is 0.4. If it is sunny, then there is 40% it's become cloudy the next day. So 0.4. And if it is sunny today, there is 20% that is rainy the next day. So 0.2. And so on and so forth. You analyze like that, the information is given to you, and you now put the information in this stochastic matrix. Right? So I'm going to fill out the rest of the matrix. So this is 0.25, this is 0.35, this is 1.4, this is 0.2, 0.5, and 0.3. Okay. Now, again, you may want to double check the sum of each column and make sure that will add up to be 1. Okay. And the initial state of these 3 states, or the initial matrix. So the initial state matrix, my X0 is equal to S0, C0, and R0, right? At the beginning, that you're going to start with the day of a raining day, right? And I'm gonna say that, so this is going to be, I assume that this is going to be a Thursday, right? So the states of the weather on Thursday, right? Because the day that I'm recording this video is on the Thursday. All right, so now you want to know what is the state of the weather on Sunday. So what is the value of X that I want to calculate? So X0 is on Thursday, so X1 is going to be on Friday, X2 is going to be Saturday, and X3 is going to be on Sunday. So we need to do that many calculations. All right, so first, the state of the weather on Friday. So the states of the weather on Friday. Right. So X1 is going to be, right, so you're going to use the this following matrix, right? This transitions probability matrix, 0.4, 0.15, 0.2, 0.4, 0.35, 0.5. This is 0.2, 0.4, 0.3, and you're going to multiply this with 0, 0, 1, right? So this tell you that okay, this is on Sunday, and that's why I'm going to set this x0. If you choose another day, you can set x0 to be any day whatsoever, right? So don't worry about that. This is the fact that today is, or Thursday is a rainy day, right? That's what we're going to start with. And we use this matrix multiplications to calculate the state of the weather of the next day being Friday. So you're going to get, right, if you do the calculations correctly, you get 0.2, 0.5, and 0.3. Okay, so that's for the weather on Friday. So there is 20% chance that it's raining day on Friday. 20% chance that would be sunny on Friday. 50% chance it's cloudy on Friday, and 30% chance is going to be rainy again on Friday. Okay, now we move on to the next states. So the states of the weather on a Saturday. Okay, so we need to calculate x2, and we need to use this matrix as well. So I'm just going to make a copy of this matrix and then use that to multiply x1, right, which is 0.2, 0.5, 0.3. And if you do the calculations correctly, you're going to get 0.265. This is 0.405. This is 0.33. Okay, so there will be 26.5% chance that would be sunny on Saturday, 40.5% chance that cloudy on Saturday, and 33% chance that will be rainy again on Saturday. Okay. Now for Sunday, you need to calculate x3. So the states of the weather on Sunday. So that is x3 equal to the matrix multiplication between the transitions matrix and the state, or the state of the weather that you found in this case, right? So that means you multiply with x2. So let me copy this matrix one more time. And I'm going to use that to multiply with this state of weather. And if I do my calculations correctly, I'm going to get 0.273, 0.412, and 0.314. Right. So this is again sunny, cloudy, and rainy. Right. So I can answer the questions that what is the probability, or what is the change that will be sunny on Sunday. So I can answer that the probability that it will be sunny on Sunday is 27.3%. Okay. So again, what we have done so far in this two example is to calculate the different states, or the probability of the different state given the initial informations, given the transitions matrix of transitions probability. Okay. And again, you can, instead of using this one step at a time calculations, you can use the end state state matrix to calculate for x sub 3. Right? Also, what you can do is you can calculate x3 as p cube times x sub 0, or this matrix. Let me just copy the matrix. So you want to raise this matrix to the third power and then multiply with the initial value. And then you will get the same value, x3, as we obtained here. Okay, so I'm not going to work out the details of this because it's more troublesome to do 3 multiplications, the multiplication of 3 different matrices at this stage. Instead, I'm going to do the calculations for one state of the weather at the time. Okay, so that's it for the example for this kind of problems. Now we move on to the next problem is related to the steady state matrix of a Markov change. The idea is that if you let the simulation, if you have a simulation, and you let this run to a certain time for a long time, will it get to a steady state? That means the value that you obtain remain the same as you run the simulation for a long time. Okay, so the steady state, that's what you want to capture, right? So the steady state is where the state column matrix, right? So that is x1, x2, x3, so on and so forth, converges to a particular column matrix called the steady state matrix, right? And you name the, depends on the book, but for this textbook that we are following, the steady state matrix using the notations x bar, like this, again, to indicate the steady state matrix. And to calculate for the steady state matrix, what you need to do is to form the following equations to calculate x bar. We need to solve the following equations. X bar equal to P times X bar. For P, again, is the stochastic matrix or the matrix of transitions probabilities. We'll see that in the example later. Now, another name is, we have another definition, it's called the regular matrix. So the regular matrix is that for some integer k greater than 0, so for some positive integer k, on entries p raised to the power k are positive. So meaning that should be greater than 0. So that means none of the entry in this matrix p raised to the power k are 0, right? Only positive value, right? No 0 remained in the calculation of p raised to the power k. Okay, so here are some example of regular matrices. So the first example is that I have the following matrix. So the matrix of the form 0.7, 0.15, 0.15, 0.20, 1.2, 0.8, 0.15, 0.1, 0.05, 0.7. And I say that this matrix is regular because p raised to the first power is or has only positive entry. The next example I can have is the following matrix p equal to 0.5, 1, 0.50. Okay, So there is a 0 in the matrix, so P1 will not has positive entries, so P1 will have a 0 entry, so that is not the regular matrix. But it still be fine to be a regular matrix because, so this is a regular, because P square equal to the following matrix: 0.75, 0.5, 0.5, sorry, 0.25, and 0.5 has only positive entries. Okay, and the last example we want to look at is the following matrix: 1/3, 0, 1, 1/3, 1, 0, and 1/3, 0, 0. Right. This matrix is not a regular because every power of P has 2 0 in its second column. And we can actually verify that by doing out calculations of P squared, P cubed, P to the 4th, so on and so forth. We don't have to work out the details for that. I just want to give you the example for to help us classify that a matrix, or the matrix of transition probability can be also be classified as regular matrix or not. Okay. Now moving on to the following example, this is where we're going to actually calculate the steady state matrix. Okay. So the question is, find the steady state matrix of the Markov change whose matrix of transitions probability is the regular matrix here. All right. So I'm going to define that, let X bar be the steady state matrix. Right. So X bar is equal to X1, X2, and X3. Why are 3 entries here? Because this is a 3 by 3 matrix. Then we look for X bar such that P times X bar equal to X bar. So that is how you set up the equations to get the value of X1, X2, and X3, or in short, X bar. So that is when you take the matrix P, 0.7, 0.15, 0.15, 0.2, 0.8, 0.15, 0.1, 0.05, 0.7, and then multiply with X1, X2, and X3, and set that equal to X1, X2, X3. Okay. All right, so now on the left-hand side, we're going to do matrix multiplications to obtain 0.7 times X1 plus 0.15 times X2 plus 0.15 times X3 equal to X1. That's the first equation. The second equation is 0.2 X1 plus 0.8 X2 plus 0.15 X3 equal to X2. And the third equation is 0.1 X1 plus 0.05 X2 plus 0.7 X3 equal to X3. Now you have a system of 3 linear equations with 3 unknowns, right? And I'm going to combine like terms and obtain the following homogeneous system. So I'm going to move X1 to the left-hand side, X2 to the left-hand side, and X3 to the left-hand side, and I get negative 0.3 X1 plus 0.15 x2 plus 0.15 x3 equal to 0. The second equation is 0.2 x1 minus 0.2 x2 plus 0.15 x3 equal to 0. And the third equation is 0.1 x1 plus 0.05 x2 minus 0.3 x3 equal to 0. So here's the system that we just obtained. Now I'm going to use Python to find the solutions, somewhat find the solution of x1, x2, and x3. And I understand that we have many concerns about using Python for the first time. A lot of you has raised that questions. I find that Python is extremely useful for us as a tool to help us solve this kind of a problem because, okay, it's very simple to do it by hand for a system of 2 equations, system of 3 equations, but what if we have a system of 4 equations, 5 equations, and more than that, right? So it's become very challenging. The problem become very complicated to solve everything by hand. And therefore, using or knowing how to use Python become a very useful skill to have, not only for this course, but I hope for the future as well. So moving forward, of course, I'm going to modify the homework assignment and the lecture notes so that I'm not going to use too much of Python code. The code that I'm just going to use is the one that we already have for the previous lectures. Okay, so for instance, for this particular system, what I'm going to do is I'm going to just basically copy what I have in lecture 3 and paste this into lecture 7. And I'm going to use this for my example 6 in lecture 7. What I'm going to do is to create a matrix or the augmented matrix of the system, right? And I just basically modify the following code. So minus 0.3, this is 0.15, this is 0.15, and this is 0. So that's the first row. The second row is 0.2, negative 0.2, 0.15, and 0. And the third row is 0.1, 0.05, negative 0.3, and 0 as well. And everything remains the same, right? The only thing that I change is the augmented matrix, right? Or the entries in the augmented matrix. Okay, now I hit Shift Enter, and it gives you the reduced row echelon form of the matrix A. And I'm going to copy that into my lecture note. So the reduce row echelon form of the system of the augmented matrix. Augmented matrix of the system is, right, so you have that going to be 1, 0, negative 1.75, 0, 0, 1, negative 2.50, and the bunch of 0 in the last row. Right. So this augmented or matrix or the reduced row echelon form tell you that x1 minus negative 1.75 x3 equal to 0, and x2 minus 2.5 x3 is equal to 0. So in this case, x3 becomes the free variable, but hold on to that. Let's solve for x1 and x2 in terms of x3. So x1 equal to 1.75 x3, and x2 equal to 2.5 x3. There is one more conditions that we haven't imposed into the problem yet. That is the value or the sum of x1, x2, and x3 has to add up to 1. this normally not going to happen, right? Normally what we have for the system is that the system has infinitely many solutions. Then we can write down the solution set by let x3 equal to t, right? For t is any value. However, we are dealing with Markov chain and also the matrix of transitions probability. And because we're dealing with probability, one of the conditions for the matrix P is that, or the state matrix is that x1 plus x2 plus x3 equal to 1, right? But we have that x1 plus x2 plus x3 equal to 1. So therefore, we're going to substitute this value into the equations. We get 1.75. Well, let me be careful here. Then substitute x1 equal to 1.75 x3 and x2 equal to 2.5 x3 into the equations. We get that 1.75 x3 plus 2.5 x3 plus x3 equal to 1. A quick calculations give me that x3 going to be equal to 0.1905. So I'm just going to choose 4 decimal places. Okay, now with x3, we can substitute back into x1 and x2 to obtain the solutions of x1 and x2, right? Then x1 equal to 1.75 times 0.1905. And this is going to give you 0.3333. And x2 is 2.5 times 1.905. 0.1905. This is equal to 0.4762. Therefore, you conclude that the steady state matrix is, so x bar is equal to 0.3333, 0.4762, and 0.1905. Okay. So that's it for me for this particular lecture. In this lecture, we look at one applications of matrix operation, and the matrix operations that we have used a lot so far is the matrix multiplications. But of course, we also use the technique of solving system of linear equations, right? We form the augmented matrix and obtain the reduced row echelon form to find the solutions of the system. Okay, so that's it for me. Let me know if you have any questions. Thank you.